that during the presentation. So I'll turn it over to you guys and feel free to start when you're ready.
Okay, well, good afternoon or good morning, everybody. Thank you for joining us today. We're going to talk about managing train data with HMS. It's something that's been brought to our attention that we don't necessarily disseminate the best potentially to our SWIMS community. And so today, Matt and I are going to go through some of the tutorials and guides material that the HMS team has spent a lot of time preparing, just to bring it to a broader audience, as well as kind of trying to convey some of the information we thought would be most pertinent on this topic to the SWIMS community. Okay, and so why we thought this was important. So the main topic for this was particularly to reduce your the file sizes for HMS. And so when you do that, it also increases our or decreases the amount of time it takes for us to create a forecast. I mean, for when you use SWIMS to create a forecast alternative, it copies that entire model over. And so if we can limit how much is in that folder, we are therefore decreasing the amount of time it takes to create the forecast. And then with this, we also took some of the similar idea to bring out how to utilize some new spatial results in HMS. So they've added a lot of fun features within the HMS interface directly to review results. And so today we're going to go through a brief PowerPoint, just kind of highlighting everything. And then we're going to either get into demos or just more of a discussion talk kind of about the ideas. So we're going to start with georeferencing existing models. And then we're going to talk about how the DEM resolution will impact creating your HMS model, both in the resolution and how much the results vary, but then how long it actually takes to compute that with varying computer parameters. And then we'll get into how we'd suggest reducing your model's footprint and looking at spatial results. Okay, and then I think Matt's going to take over for the remainder of the PowerPoint section.
All right. Thank you, Alex. Can you hear me okay?
Yes, sir.
All right, before I get going too far, and I promise we just have a few slides and then we'll move into the demonstration. The projects that we're going to demo today, you can find those here. These are in the main, so if you go to the HMS webpage, I forgot you don't have this PowerPoint presentation yet. Let's just go to HEC. So HEC, and then if you go to the HMS page, and then under documentation, you should see, oh, I'm wrong. It's under the training material link. Once you go to the training material link, you can see tutorials and guides. And then under tutorials and guides, most of the examples that we're going to walk through today, they live in the GIS tutorials and guide space. So I think one of them Alex is going to go through is at the top here. So how to georeference an existing basin model. And then at the bottom there, we'll go through comparing GIS processing runtimes and then reducing your project's footprint. Okay. All righty. And then an overview of the GIS menu. So this really started becoming available in version 4.6 or so about 2 years ago. And so I know a lot of projects have already been created since the GIS menu came into being. And so those are the projects where you'll need to run through the steps to georeference those projects. So you can interact with polygons or you can utilize the new spatial results options. Let's see here. If you do use the GIS tools in HMS, they replaced the old GeoHMS tools. If you never had to use Geo-HMS, then good for you. That library was designed by Esri, or those tools were designed by Esri with our input for sure, but you'll notice that the workflow that you have available to you in HMS, it is so much more streamlined. There's just one menu that you're going to go through to georeference your basin model, work with the terrain data, get your subbasins and reaches delineated. And then there's also other tools to compute your watershed characteristics and then other information that you need for any geospatial type work. All right, and then those are the tools on the GIS menu, some of the files that get created for you. If you ever open up HMS with File Explorer and go to one of the project directories, you should see a number of folders that look like this. The Maps folder, this is where I like to store all of my background shape files. If you put those shape files in that Maps directory, then HMS is going to use a relative path name so that anytime you copy your project to another computer, all of those will be saved with that project. They're contained, and then HMS will be able to easily find those background shape files. That's the Maps directory. The GIS directory, this is the directory that HMS automatically creates, and then any of those raster data sets or any of the other GIS layers that HMS creates, the program is going to automatically save those in the GIS folder. And then one other file to point out, you're probably familiar with the .basin file. So this Mahoning_Creek.basin file, this is where HMS saves information from that basin model. So information, parameter values for your subbasins, reaches, and so on. So that's information that you enter. And then there's also going to be this sidecar SQLite file. This is the file that HMS saves all the geospatial information for. So if you've georeferenced your project, then you're going to see inside of the SQLite file all of the polygon information, also your grid cell files. That information is going to be saved to the SQLite file. All right, and then let's dig in just a little bit. So within the GIS directory, you should notice there's going to be a separate directory for each basin model. And then for each of those basin model directories, that's where the program, again, is going to save the raster data sets. In this example here, here's the elevation.tif file. So that's the terrain data as you loaded it into the basin model. And then when somebody ran through the steps to delineate the subbasin elements, the program is going to automatically create the flow accumulation, flow direction, and then those other raster data sets that you see there. So that's part of the whole delineation process. Okay, here, let me pause there for just a second. Any questions out there? Okay. And then if you do have them too, you can enter those questions into the chat area. All right. So Alex is going to talk through this in just a minute, but what I mean by georeferencing an existing model. So if the model was developed more than a couple of years ago, then what you'll see if you open up that model, you're going to see just those element icons. And that's the way that people used to interact with HMS. You would drag and drop those element icons into the basin model, connect them one by one to create your hydrologic network. And in this example right here, we have 3 subbasin elements here connected. And these 2 are connected to a junction. Then that junction is connected to a reach, a straight line reach. And then we have the outlet down here at that junction. So that's the old way of doing it. Alex is going to show you how to use a shapefile. So if you have a shapefile for subbasin elements and the names within the subbasin shapefile correspond to the names in your HMS basin model, then HMS will import that spatial information, the polygon boundary for those subbasin elements, load that into your HMS basin model, and now you can interact with your subbasins using polygons. You can click on a polygon and then enter the parameter information for that subbasin element. Same type of thing for the reach. If you have a shapefile that has reach segments and those reach segments have the same name as reach segments in your HMS basin model, Then you can georeference those by importing that information, and then HMS will draw those reaches with polylines. Okay, so after we go through that one, then we'll touch on another example project where I like to show the benefit of reducing the original terrain that you use to delineate subbasin elements. A lot of folks like to use the smallest terrain or grid cell size possible. So I've seen people try to use 2 meter or 5 meter DEMs. And that's good. HMS can chug through those for sure, but it's going to take a long time. And what I want to show in this example project is if you have different terrain grid cell sizes and you have different types of computers that are available to you, different number of cores, different amount of RAM, then what's your processing time going to look like with those different file sizes? And does it matter, right? If you have a 90-meter terrain versus a 30-meter terrain, are you going to be able to delineate the subbasin boundary that you need to? Or are you going to lose so much information that the subbasin boundary is not going to look like it should? So we'll go through that. Oops. And then finally, reducing your model's footprint. So this is really important so that after you initially create that project, you have those different basin models. Each of those basin models is going to have its own terrain data. And then every time you create a copy of a basin model, it's going to keep copying that terrain data to the new project's GIS directory. And so there are ways, there's things that you can do to overcome copying so much terrain data over and over and over so that when you need to pass the project from your computer to somebody else's computer, you don't have to wait an hour while it just zips up and then uploads to some FTP site somewhere. So there are ways to reduce the footprint, and then Alex will walk through those. And then the last thing I want to touch on too is spatial results. So after you go through the steps to georeference your project, and you also use the new discretization method that's in HMS, the one that I would suggest folks use is the structured discretization method. If you do use those options, then you can turn on your spatial results and then visualize really important information from different simulations. You can visualize incremental precipitation, snow water equivalent, temperature across the watershed. You can see these computed results either on a gridded basis, if you're using the structured discretization, or lumped or averaged over the watershed if you're not using structured discretization. So these are the types of output that you can visualize spatially on the left. Also, you can visualize your calibration metrics. If you have observed SWE in your project, then you can visualize how well the model is performing when matching the observed SWE, or also observe flow. So there's ways to visualize how well the model is performing in space. And then there's other controls here with spatial results. You can animate the spatial results. You can view the minimum and maximum grids or results. There's also tools for editing the display properties, capturing and exporting animations or GeoTIFF files. So real quick, so if we click on this one, this shows you an example spatial result animation for one of the new features in HMS for interpolating point rain gauge information. And so you can visualize, well, of course, you're going to see the heaviest rainfall here that's lining up with those gauges that are being used for the interpolation process. But that's one way to visualize results there. And then other ways to visualize the results, you can always right-click within the basin model map area and open up any spatial plot for a specific grid cell. And in this figure here on the right, we see this is the snow water equivalent for grid cell 1014, 1031. So you can get that detailed information if you want to. You can also visualize the time series or export it as a table and then plot it in another tool if you need to. And then next to the last slide here, this shows you the spatial results. This is the editor for changing the look and feel for the spatial results. And what we're plotting here in this figure, this is the Nash-Sutcliffe efficiency for flow. And what the program finds is it finds those locations with observed flow, And the way this model was set up is all of those locations with the red halo around the icon, those are locations with observed flow. The program looks at the Nash-Set cliff efficiency at those locations, and then it's going to shade in the polygons, the subbasins upstream, based on the model performance that's defined in this table right here. Right, so for any subbasins or areas where the Nash-Set cliff efficiency score is less than 0.5, then the program's going to draw that as a red area. If the Nash-Set cliff is above 0.8, you're going to see the lighter green area there too. So it's just a quick way to quickly visualize which portions of your watershed do you need to spend more time calibrating or adjusting model parameters. And then finally, and before I turn it back over to Alex, if you go to the HMS documentation space, you'll have access to those tutorials and guides. There's quite a few in there. So just search through those for any topic that might be interesting to you. And then also under the training link here, there's access to the recent basic HMS class and part of the dam safety class that we gave just a few months ago. All right, I'll stop there and turn it over to Alex.
Sorry, I was muted. Thank you, Matt. Is my screen coming through okay?
Yep.
Okay. So we're going to start off with the georeferencing listing. Like Matt said, we're just following these tutorials and guides that the HMS team has put through. And I would suggest if you haven't, go through it. And if you have, still recommend checking it every so often. There's even a new tutorials to check out section. And so there might be something new or that might pique your interest in there. So all we're going to do is associate the shape files with the subbasins. And so a lot of times, especially in the older models, we'll usually have something, we usually just do something like this with the older ones, to where it's just a shape file on top of the HMS. I've seen this process is a little bit updated and it's a little bit slower too. For this use case, it's not going to be significant. We're using a very simplified example, which is a couple of subbasins and a singular reach, and so you're not going to notice it as much. But I'm trying to get away from this older approach of visualizing, because this did help kind of see the domain and figure out what the subbasin actually covered. But there is better ways of doing this now. So I'm going to go ahead and remove this. And so we're going to utilize the GIS functions through here. So even though this model was not generated using the GIS functions, and therefore we don't have terrain or anything like that in here, so we don't have all these options, we do have these options at the bottom. And we're going to use this georeference existing elements. So this allows us to bring in the shapefile and associate it with the subbasins. And so we have the option between the subbasins and reaches. We're going to do both. We'll start with the subbasins though. So we'll just select the subbasins. And then we look for the file name. Is it under? Okay, no, it's just under maps right now. And so then we'll go to subbasins. If I wasn't just here, I would also recommend still making sure your directory is right. I know on my computer I have a lot of subbasin shape files, and so I have tried using the wrong stuff before. So it's just nice to double check every so often. So we'll hit next. And so this interface is showing the attribute table that you'd find in GIS. So this is a very simplified example that's been pampered for this explicit use case. Usually you'd probably have a lot more attributes. You might even have multiple name categories. So it might be good to open up your GIS application of choice, QGIS, GIS Pro, whatever it may be, and just view the attribute table of your shapefile of interest. But here again, we only have one option, and I know it's the one that I want, so I'll just hit finish. And so voila, we already have these subbasins in here. And so now it might not seem very much different comparatively to when I just had it as in a map layer, and it's actually still, now it's in the map layer as well, and I can turn it off and turn it back on. But now it makes it a little bit easier to navigate. Again, if I were to be zooming around the model, it's a little bit quicker now. It's I'm a person that really values my time, so if it takes even saves me a couple of seconds when I'm doing it repeatedly, I find it very useful, and that's where I find this to be. But as well, now I can click anywhere in the subbasin shapefile, and it selects it for me. I don't have to go through and find the icon and make sure I hit that. Now I just have to hit the general area. So I will say the name matters significantly in this case. When we go through this process, in this example, it's an example, so everything is just like you'd want it. In real cases, there might be somebody in the HMS that has it labeled Stump Creek. The GIS might be Stump CRK. And if that's the case, this subbasin just isn't going to import, and it'll just stay this little icon. And so then all you have to do is open your GIS application, go through and find the subbasins that didn't get generated, and go and see the attribute that you used and make sure it's named correctly. They're usually pretty big gaps, but sometimes you might have a small subbasin that's just kind of missing. And so takes a little bit of time, but in my opinion, it's well worth the time to go through and actually georeference these subbasins. And then we're going to do the same with the reach. In this case, it's set up the same way. So we're going to reach subbasin. Next, again, just one attribute. And so now the reach is georeferenced. So this, for me, helps me understand more so of the stream. Now you can see the meander versus just the straight line. And so I'm a very visual person, and so this helps. And just like you could before, you can just click on the reach and interact with it. And that's all for the georeferencing the existing items. Again, fairly just a couple of steps, but I feel like it's well worth the time to go through and do it. And then personally, I usually have to do it twice because I have a lot of subbasins that won't be named identical, and so you just have to go through again. But when you do, when you have to do that, you can go through and just select it again, and HMS just asks you if you want to replace it. So it's trying to make sure that you want to do it before you go ahead and do it, and we can just replace it and it'll overwrite. And at that point, ideally, all of the subbasins you were mentioning earlier are now showing as a shapefile. So are there any questions with regards to this before we let Matt talk about the DEM size and processing? And I don't know how to see chat. So okay, so I think we're good. So Matt, if you want to start the next section.
All right. Yep. Let's see here. Two things I jotted down real quick. There is a limitation. Well, let me share. There is a limitation with shapefiles whenever you do georeference an existing project. You have to make sure that the shapefile has the same projection as the basin model. That's not the case with terrain data. If you've already set the projection for your basin model and then you load in the terrain, what HMS does is it is going to create a copy of the terrain and reproject it into the basin model's projection. But it doesn't do that with shapefiles. So that's one thing to watch out for, is if your basin model is in state plane projection and you try to georeference those elements, then you have to make sure that those subbasin shapefiles are in the same state plane projection. Okay, and then another thing real quick, I just learned this today. Somebody was asking a question about changing the projection for an existing project, and this is new for HMS 410. Prior to 410, if you created a basin model, you could not change that basin model's projection. Now with 410 and newer, what you do is, let's say you open up your basin model, you don't like this projection, you need to reproject it. You go to the GIS menu, you choose coordinate system, and then you can browse to a new projection file, right? So I typically store those in my map directory, and then there's a PRJ or projection file. You choose that file, and then it'll show the new projection in this window right here. And then you click the set button, and the program will reproject all of the spatial information that HMS displays, and then it also reprojects all of the information in the GIS directory as well. So that's a big time saver. All right, so let's talk through comparing GIS runtimes with different size terrain models. I get this question a lot, and I've struggled through trying to download big projects, right? I mean, how many of us during COVID times were working at home and somebody was trying to get us a 20 gigabyte file, and it literally took a whole day to get that file from one machine to the next, right? And so part of that is because the terrain data for subbasin delineation, those file sizes are rather large. And the whole point of this example here is to show you that you don't have to use super detailed terrain data to delineate subbasins. You do for your river hydraulics. So for RAS models and developing detailed inundation maps, for sure, use the highest detailed terrain data that you can. But for subbasin delineation, you don't need super detailed information. All right, so in this example here, a couple of different machines that I used. One machine had 4 cores, 8 gigabytes of RAM. That was the lower end computer. And then the higher end computer had 8 cores and 32 gigabytes of RAM. One thing I want to point out too with HMS, you get to choose how many processors HMS uses for certain things. If you go to the Tools menu and then Program Settings, and then I believe it's under Defaults. Go to the Defaults tab. There's an option for number of cores, and you can choose that based on the number of processors on your machine. Right now I have 12 cores chosen, and then the program's going to use that specifically for all the GIS steps. The program's going to use the number of cores that you specify here. And then for any of the 2D flow computations, the program will use multiple cores. For other computations, I believe the program determines that outside of the number of cores that you specify here on this editor. All right. All right, so those are the different computers that I use, and then the different terrain models. The 30-meter terrain model, about 1.3 gigabytes in size, and then resampled that down to a 90-meter terrain model. File size for that, 127 megabytes. All right, and then also what I always like to do is I like to burn in information from the National Hydrography data set. So I always take a few minutes, download the detailed stream information, and then also download any of the HEC watersheds. So based on the size of the watershed or study that I'm working on, I might use HEC 10, HEC 12, HEC 8, use the appropriate size. And then I like to use the the terrain reconditioning tools in HMS to either burn those streams into the terrain model or also impose walls where those HEC boundaries live. So you can do that with the reconditioning tool. All right, and then if you scroll through other tables in this example, you'll see the processing time it takes for HMS to chug through different steps in the whole delineation process. For example, right here, let's see, let me zoom in just a bit. There we go. Right here for the pre-processing sync step, for the 30-meter terrain on computer 1, it took 227 seconds. The 90-meter terrain on computer 1, just 13 seconds. So you can see a big time savings just in using a coarser terrain model. But then using different machines, right? Machines with more memory or more processors, you can see, well, for the 90-meter terrain, it doesn't change that much. It's already really fast. The only benefit that you get with a better machine is for the larger terrain model. Okay. So I'm not going to go through all of these, but you see generally the same type of results, right? So better machine, faster processing on the 30-meter terrain model, but for the other terrain models, the 60 and 90-meter terrains, those are already pretty fast, and you don't see as much reduction on those for some of these processes. All right, so let me just jump down to where the table summarizes the processing time for all steps. Let's see. There we go. So here's the final processing time in minutes. So this is for all of the steps to get through your initial subbasin delineation. You're looking at about 40 minutes on the first computer versus 2.4 minutes. And then on the best computer, about 30 minutes versus 2 minutes. You might think, hey, that's not bad. I can live with doing this one time with a really detailed terrain model and it taking about 30 minutes. But from what I've experienced over my career, you never go through it just once. There might be a mistake. You might have to go run through it a couple of times. Somebody might review your model and ask you why you did it that way. You should consider this. And so I think on most projects that I've gone through, I've had to go through the delineation steps at least 4 times, maybe more. So that's why I like to use as coarse of a terrain model as possible, given the constraints of the problem, right? If I need a lot of subbasins, then I might use a smaller grid cell terrain model versus if I just need a few subbasins and it's a rather large area, then consider using a 60-meter terrain model. Okay, so that's the processing time. And then what I wanted to jump through next is, well, does it matter? Do you get different delineations based on the terrain cell size? That's what you get to on this table right here. Just want to make sure. Yep. So for these, this shows you different subbasins in the project. And you can see the drainage area for each of those subbasins for the different terrain models. So here's your 30-meter terrain model, 90-meter terrain model. And then the columns on the right, those show you the percent difference, right? So the percent difference in drainage area between the 30-meter and the 60-meter terrain. Percent difference in the 30-meter terrain and the 90-meter terrain. So what you see here is there's a really small difference in these subbasin areas as long as you burn in that stream network, a detailed stream network. I believe the next table is going to show us if you don't burn in a detailed stream network, instead you burn in a coarse stream network. You're going to notice larger differences in the area here. Again, this is difference between the 30-meter and the 60-meter terrain. You're going to notice some of these areas, here's a 12% difference, right? So the 30-meter terrain had a drainage area of 2,885, the 90-meter 3,240. Okay, so the point of this whole exercise here is to show you if you do burn in a detailed stream network, you're probably going to get similar drainage areas regardless of the cell size of the terrain model that you use. Okay, let's see, what else? Yeah, another stream network. And then also at the bottom of the example here, you should see different characteristics. Longest flow path, what's the difference in the longest flow path? When you use these different terrain files or terrain grid cell sizes. And you'll notice that the differences do seem high here, but I forgot to take everything back to feet. This is differences in miles, so that's going to explain some of the large amounts here. But even regardless of that, I mean, 76 miles for the longest flow path length here versus 62 miles. So that's quite a bit of a difference for sure. One thing to be careful of, though, is if you do use a coarser terrain model, you might not get the best information for your characteristics. So there are some tips and tricks that you could use to use the coarser information to delineate your watershed, but then use the detailed information, detailed terrain model to compute your subbasin and reach characteristics. So if you're interested in that, just let me know, and I can pull together that information too. Let's see. Yeah, reach length and reach slope wasn't that difference between the different terrain models. So those percentages are pretty close. All right, so I'll stop there. Any questions or comments out there? All righty. All right, Alex, turn it back over to you.
Thanks, Matt. So now we're going to discuss a little bit about the GIS files that are generated in HMS. This is more so of what we were hoping to cover. We just tried to sprinkle in some more things that we thought would be applicable and useful for everybody to know. And so this is going to be covering reducing your file size. And so right here I have a HMS model open. We have 3 basins. So we have a delineation, 94 and 2018. And in this, we use, in this HMS model, sorry, we use the terrain to generate the entirety of the HMS model. So if I go up here, kind of see that we've have all these options and already ran through them. And so then if we go into the GIS folder of HMS, you'll see that we have a folder per each basin. And so this example has already been edited a little bit. And so, and these, the 2 specific basins, they've been trimmed down to just the terrain. But then let's start looking at this delineation one. And so this is all the files that are, with the exception of the terrain, all these files are generated using the GIS procedures in HMS. And I kind of like knowing generally where files are generated from or what processes. And so as you progress, the pre-processing tool does the 2 sync TIFF files. And then the pre-processed drainage generates the DMS8, the flow direction, and the flow accumulation TIFF files. And then they identify streams do the stream bin and stream TIFFs. And then when we delineate, we get these 2 SQLite files. So again, as you can see, most of this is generated as we progress. And so none of these files in File Explorer are too big by themselves. But then when we go out here and just look at the properties real quick, we're looking at about 150 megs. And this one that's considered finished for this example is sitting at 3 megs. And so we're looking at close to 142 megabytes per basin that we can chop off here. And so when you think about it, the per basin, you can see it's really adding up. So let's talk about how we actually get rid of these files. So this is actually one of the few times I feel like that will tell you to actually work within the File Explorer and not in HMS itself. So for this example, the user for the 94 and 2018, all they did was go through and select everything and unselect elevations and just deleted it. So this does make it to where HMS doesn't necessarily recognize it. And so when we're in this delineation, we go to view map layers. We have all of these options, and then we can select flow accumulation and it'll generate. When we switch to one of these modified basins, and we go to the same thing, we still have all the options, but when I go to flow accumulation, it doesn't do anything. So that's one thing to keep in mind. Since we're not doing it through HMS, it doesn't necessarily know that these files are gone. It just won't generate anything whenever we when we go there. But the thing about the way we do this, so if I take this flow accumulation. Hopefully I'm grabbing them all. And I copy and paste them back into this 94. Now I should be able to see it. Yeah. So that's one of the better things about this process that we're telling you to do with doing it out here. In that I would recommend, from my perspective, I don't get into HMS to look at a ton of results with what I do in the CAVI. And so this modeler wanted to keep elevation because it helped them understand and see the results better within HMS. I might suggest even getting rid of this for some projects, not necessarily all of them. It's still a case-by-case thing. But I spend all my time in the CAVI, even when I'm calibrating HMS. And so to me, this is just additional space. And but before you do that, I'd highly recommend to archive at least the GIS folders, if not the entire model, to make sure you can come back to it. So that's one of the purposes of, in my perspective, from this keeping this delineation basin here. We have all of this GIS data, and like I just showed, I was able to move it directly into this other basin and able to use it again. But if we were to, in this case, delete all the GIS data, we're looking at close to half a gigabyte of data. And I know I have decent internet, but I would still be thrilled to see half a gigabyte of data that I'm probably not even going to use be removed from a model when I'm trying to upload it to any shared drives, or if I'm trying to utilize team modeling and pushing it to a SWIMS database. To me, half a gigabyte can mean quite a bit of time. But again, archive, save copies of everything. We strongly recommend, but for upgrading models to archive even too as well. So yeah, just make sure you back up in case something goes wrong. Is there anything you'd like to add, Matt? I feel like there was more talking points, but my mind just slipped.
Let's see here. Yep, there are a few things to add. Let's say you do delete those terrain files, and then you come to the conclusion, oops, you need to rename a subbasin, or you need to redelineate a specific area within the project. Then what you can do is you could run through the terrain pre-processing step again and regenerate those files, or like what Alex was showing, you could copy and paste those back in there, and then make those changes or run through those steps to either rename or do a delineation or redelineation. One of the things to watch out for too is if you do rename subbasins, you do need to rerun through. Go to the GIS menu for me, Alex. You have to regenerate those grid cells for the structure discretization. So if you go to the bottom under compute, and then you'll see like grid cells. Right now it's grayed out for Alex because he's not made any changes. And so the grid cells that already exist are still valid. But if the name changes or redelineations, then you have to recompute those grid cells. And then the program really does need the flow direction and flow accumulation and D8 grid or raster layers. And if they don't exist, then you'll have to recreate those before the program is able to regenerate those grid cells.